All right. The last thing we're going to do here in electrostatics before our charges start moving more is talk about two particular situations that are kind of important, and there's some interesting physics to how they work. So we're going to talk about the electric fields created by a flat plate and by a sphere, a charged sphere. So the reason we're doing this is because if we can get a sense of how charged spheres work and flat plates work, those are both really useful things. But in order to do that, we have to think about how a conducting object behaves when it's in an electrical field. Remember, this is my conducting object. So let's say this is a cross section of a rod, like a copper rod, like a nice conductor. And we've got a steady charge over here of a positive charge or positive voltage, and we have a negative voltage over here. So we've got an electrical field. If these blue lines, they just point to where a positive charge is going to go, right? So if I let go of a positive charge here, it's going to fall along that line. Um, what happens within that conductor? Well, the conductor has free electrons in it. And those free electrons are going to be attracted to the positive side. So they're going to come over here. And that's going to mean that I have an imbalanced charge, right? So I'm going to have more protons over here and a positive charge over here. Or my protons aren't moving. I just don't have as many electrons. Okay. Now, at some point, these stop moving, right? Really, actually, quite quickly. I put that conductor in there, and those electrons are going to fly there, and they're going to stick. What does that mean that they're not moving? Well, it means there's no field in there, okay? Because if you have a charge in a field, then it's going to be moving. Our field is newtons per coulomb. I put a coulomb in there, I'm going to have some newtons. I'm going to have a force. Well, here, essentially, this is creating an internal field with the negative over here and the positive over here that contradicts the larger field outside the conductor. And that means that there's no field within the conductor. Okay, so that's sort of an interesting result when we put a conductor into an electrical field. What does that mean for flat plates and for spherical charged objects? Why does this matter? Well, in a spherical charge or a spherical conductor, we get some nice symmetries here. Okay, in a sphere, for instance, the charges are going to move as far away, whether it's positively charged or negatively charged. They're going to move as far away from each other as possible. Okay, so they're going to fly to the edges here. And that means they're going to be equally spaced around the edge of our sphere. Similarly, in a flat plate, I've got positive charges over here on my voltage, on my positive voltage, and negative on my negative voltage. They're going to spread out as much as they can in order to get as far away from each other as they can, because they don't like each other. That won't be necessarily true quite at the ends, but in the center of the flat plate, they're going to be very nicely spread apart. That is useful to us. It means, on the one hand, that a spherical conductor acts as a point charge. So we know what voltage is for a point charge. We know what coulombs, the electrical field for a point charge is. And so any sphere that's a conductor, we can treat as if it's a point charge. So if I have a copper ball, it's going to act exactly as a point charge would, with that point charge right at its center. So that's very useful. And then for a flat plate, the fact that these are nicely spread out, the charges are nicely spread out on your flat plate, allows us to make a super convenient, nice horizontal field here. So our electric field is all arrows pointed all parallel to each other. And that means we have a really controlled space in here for various applications. We can calculate that electric field too as simply being the voltage divided by the distance, right? This is just V equals E delta S rearranged a little bit. and it tells us that our electrical field is the voltage divided by D. So what does that mean about flat plates? If I move these plates farther apart, what happens to my voltage? Nothing. Your voltage stays the same. Okay, that's kind of like your elevation, right? I'm just because I'm uh, moving my, this is at 0 meters and this is at 10 meters because I'm on a ladder. I move my ladder 10 feet that way. I'm still at 10 meters. The difference is the slope between the two is going to change, right? And that's the electric field. So when I move these farther apart, my voltage stays the same, my distance gets bigger, and that means my electrical field gets smaller. And that's why a flat plate is useful. Now, just to give you one way that you can use that flat plate, because these are very commonly used as a way to redirect charges, we can change the charge on one plate. Here we have, a given voltage on both plates. If I change the charge up here, stuff a bunch of new charges on there, I can alter my electric field. Okay, and this is actually how an inkjet printer works. So I have this clever little doohickey over here, and you can see, so the nozzle spits out some droplets of ink, and then you have apparatus that throws a charge onto them. Let's say a positive charge, right, on each one of these, so that each of the um, droplets of ink has a charge. It goes through this flat plate here, and if I change my voltage on, say, this upper plate, I can change the electric field in there, and I can direct these droplets and say, hey, droplet, you go to the bottom half of the E, you go to the top half of the E, and I get a nice letter. And so that's how a flat plate can work, and that's why it can be helpful to know and understand why those charges spread out within a conductor. And that is it for electrostatics.